I wish to welcome you all to this presentation on shadow pricing farmland environmental services. So this is work in progress, and I want to solicit feedback from you so that I can improve the paper. Okay. So this is one of the objectives that I'm pursuing in my thesis. The thesis broadly looks at the economics of sustainable agricultural intensification, with objectives on efficiency, adoption, and impact. So sustainable agricultural intensification is basically the integration of legume-based cropping practices, organic manures, and inorganic fertilizers. So this is done in order to raise farm productivity and improve food security situation. As you might be aware that the food security situation in Malawi, as well as most parts in Africa, is a challenge. So different stakeholders are looking for different strategies that can contribute to improvement of food security. So in this presentation, I'll talk about the importance of legume-based cropping systems. Then I'll talk about the methods that we use to derive shadow prices for symbiotic nitrogen, particularly the directional distance function, and then I'll present the empirical results, and I'll conclude. So before I go into details, I just want to show you two cropping practices that are a focus of this study. The first practice is crop rotation. So in this practice, usually maize or cereals in general are cultivated in succession with legumes. It is believed that there is nitrogen sparing effect from legumes, which is used by a subsequent crop, in this case maize. So in that way, it is considered as a capital saving strategy. Then the second strategy is intercropping. So intercropping is a practice where cereals, in this case maize, is grown together with legumes, groundnuts, pigeon pea, and others on the same piece of land in the same season. So it is believed that this is land saving in the sense that there are multiple crop outputs produced on the same piece of land in the same season. So practices like these are promoted in Malawi and other parts of Africa. For example, in my country, Malawi, the government has introduced an input subsidy scheme where targeted farmers buy inputs at reduced prices. So in this subsidy scheme, they have included legume seeds, maize seeds, and chemical fertilizers that are purchased at reduced prices. So you will see that this is quite important, and it is considered highly in terms of policy. So why legume-based cropping systems? As I've alluded to, besides crop outputs, legume-based cropping systems supply multiple benefits in terms of environmental services. So, for example, if legumes are included in a crop rotation, they have the capacity to suppress some weeds, for example, witchweed or striga, which is associated with maize production. So if legumes are used in rotation with maize, then they are able to suppress the disease incidence. And also, legumes fix nitrogen through the nitrogen sparing effect. They fix atmospheric nitrogen, and part of this nitrogen is used by a beneficiary crop, in this case maize. So we realize that these are mostly biological processes. They are quite difficult to quantify or value because these environmental services are not directly traded in the market. And again, even if surrogate markets exist, markets for substitute or complementary commodities, we know that in most parts of developing countries, the markets are not perfect. there are quite a number of distortions. So this together makes valuation of environmental services a challenge. However, it's still necessary that for policy purposes, we know what these services are worth. So it is important that we give an estimate of their value. So this takes me to the objective of this study. So the objective of this study is to compute the shadow price of symbiotic nitrogen. So if we have an estimate, we'll have a better understanding of what these environmental services, particularly symbiotic nitrogen, is worth. So even though the legume-based cropping systems are being promoted, studies show that not much research has taken place. Their benefits have not been shown. So this is in a way to contribute to this gap. If we have information, we can advocate for something that we know for sure what it is worth.
Just one clarification question.
Yep.
Robertson, please. You're having a look at both strategies where you have one crop and then you change it later for legumes, the rotation, and also when you're planting both at the same time. Are you evaluating both? Yes,
so we have two practices,
yeah,
intercropping
and
rotation. Okay. So how do we value these environmental services? So one way to value them is to consider environmental services as an input in the production process. So if that production link can be established, then one can attribute the contribution of environmental services in terms of change in output. For example, in terms of crop production, we can think of yield gain or incremental gross margin with and without a particular environmental service. Or one can decide to evaluate on the input side. Because of the introduction of the environmental services, there is a change in the input mix. So there is either substitution effect or complementary effect. So that change can be attributable to the environmental service. So like in this case, we are pursuing the input side, where we are talking of fertilizer savings due to the introduction of symbiotic nitrogen. So a production technology can be represented by a production function, which can be simplified in this form, or the alternative to representing a production technology is a distance function. So I should also state that there are two types of distance functions. There's the radial distance function, introduced by Shepard in the 1970s. So sometimes it's just called the Shepard distance function, and the directional distance function, introduced by Chambers and others in 1996. Both the radial distance function and the directional distance function are able to represent a production technology where there are multiple outputs and multiple inputs. But in this case, we'll be using the directional distance function for the advantage that it uses a uniform metric with which to measure inefficiency. Maybe some of these things will come clear when I show you the next slides. But just to say that with directional distance function, we can project in the input space. Okay, maybe I'll take you to the graphical presentation. So with the radial distance function, one can measure, okay, first, if producing films are efficient, they would be on this frontier. This is a production possibility scale. So all efficient films would be on this frontier boundary. But any film that is below the frontier boundary, like film A, is considered inefficient. So to measure that level of inefficiency, you can either project in the input direction or in the output direction. So for the radial or Shepard distance function, it achieves a proportional contraction of inputs or a proportional expansion of output. So you can either be on the input direction or on the output direction. But with directional distance function, you can decide to be only on the input direction or only on the output direction or both. So you can achieve both expansion of outputs and contraction of inputs. So it's for this advantage that the directional distance function is used. And again, I also said that it uses a uniform metric with which to project in the input direction or in the output direction. For example, if our projection metric is G, it means that it is going to contract inputs using the G metric and expand output using the G metric. So if G, for example, is 10%, then it is going to contract inputs by 10%, and then the distance, which is the measure of efficiency or inefficiency, is also going to reduce by the same metric, which is 10%. So this is also the property of the directional distance function, which is called the translation property, which I've just talked about. Then it's related to the homogeneity property, which is a property of the Shepherd distance function. So having looked at the graphical presentation, let's look at the mathematical presentation of directional distance function. So we're saying there are inputs, which is a set of inputs that are used in the production process, and then these inputs are used to produce a set of outputs. So together these make the technology set. So the directional distance function says that we can project in the input direction, we can reduce or we can translate the inputs, or we can project in the output direction. We can expand the outputs. So the directional distance function seeks that maximum distance with which we are projecting. In this case, we choose to project in both directions. We are projecting in the input space and output space and still remain within the production set. So this is a primary representation of the technology, the distance function, but there is also a dual representation of the technology, which is a cost function. So Ferrer and others show that there is that relationship between the primary representation, which is a directional distance function, and a dual representation, which is a cost function. And we also have a shadow cost function. So if we are working on the primary front, we can take partial derivatives of the distance function with respect to any of the inputs. So that gives us the marginal product of that input, the incremental value of that input. If we take ratios of two inputs, like this partial derivative on input xn prime and the partial derivative of input xn, we get the marginal, we get the marginal technical substitution, sorry, a marginal rate of technical substitution. So, which basically shows that there is a trade-off between one input and the other. If how much of the first input we can increase by reducing the second input and still produce the same output quantity. So in optimum, the ratio of marginal products, which is marginal rate of technical substitution, is equal to ratio of factor prices, the prices of the inputs. So if we know the price of one input, like in this case, we know the price of fertiliser nitrogen, we can use this information to compute the price of the unknown, in this case, the price of symbiotic nitrogen. So this is the approach that we are using to get the value or the price of symbiotic nitrogen. Okay, in terms of study sites. This study we conducted in Malawi. So this map is produced courtesy of Thais, my GIS expert. Thank you, Thais. So, yeah. So we visited 2 sites. One is the northern part of the country, and the other one is in the central part of the country. But both of these zones, they are within the same ecological zone. So we choose this zone because it's the major producer of maize and legumes. Then we randomly pick 300 households for interviews. So out of these 300, in this paper, we're just using a subsample of 135, where maize and legumes were intercropped or they practiced crop rotation. So we collect information on production in terms of outputs and input use. So outputs is maize and legumes. Then we aggregate together using the dollar value. And then we collect information on fertilizer use. Then we convert it to nitrogen as an active ingredient. And then we collect information on labor use, which is family labor in terms of the number of people who are working on the farm. And then to get the quality aspect of labor, we convert it to adult equivalent units. And then we also get information on costs, which is usually seed and manure and other inputs that are used. So symbiotic nitrogen is not directly observable, so we use the harvest index to compute the kilogram of nitrogen that is used on the farm. So the estimates are readily available in the literature. So we use those estimates to compute for intercropping, and then we also compute for intercropping and rotation.
Sorry, can I?
Yep.
Symbiotic nitrogen, is that some function of the planting of a legume? Is that how that's calculated?
Yes. So if they are cultivated together in association, so we're saying there are estimates that tell that if you have a hectare of legumes, this is so much nitrogen that they will contribute to the soil. Or you can work in terms of grain. So there's also that relationship which says if you have this much grain, then this is the amount of nitrogen that is left. Yeah. So I should also state that we parameterize, or we get a functional form of the directional distance function. So in this case, we're using a quadratic functional form because it has some desirable properties, like it is linear in parameters, and also it contains both the first order and second order parameters. So using that functional form, we're able to get the partial derivatives, and then we use those partial derivatives to get marginal products. So there are 2 models that I want to present in the empirical results. The first is the base model, and then the second is the bootstrap model. We also bootstrap to get a sense of variability in terms of shadow prices and efficiency. So if we use the base model, we find a mean of 0.32. So recall that inefficiency, we said, is the distance from which an observation is relative to the frontier boundary. So this is the distance, which is a measure of inefficiency. So we get a mean of 0.32 in the base model and a mean of 0.38 in the bootstrap model. So this shows that there is room for improvement. In terms of output, we can improve output using the same inputs, or we can reduce inputs and still get the same quantity of output. So 0.38 suggests that we can increase output by 38% of the mean. So remember, the mean was about $120 per acre. So this suggests that there is room for 38% of the mean to increase using the same inputs. If we project on the input side, it suggests that we can reduce the inputs by 38% of the mean input use, either fertilizer nitrogen, symbiotic nitrogen, and other inputs that are used in the production process. So using marginal products, ratio of marginal products, we get the shadow prices for symbiotic nitrogen. Again, this is the base model, and this is the bootstrap model. So we get a mean value of 0.75 in the base model and 0.23 in the bootstrap model, with reference to the average price of fertilizer nitrogen, which is about $2 per kilogram. So a value of 0.23 means that if a farm was not using any symbiotic nitrogen at all, by introducing a kilogram of symbiotic nitrogen, they are able to improve their output by 0.23. So the value that they are getting from crop production would increase by 0.23. So that's the benefit that comes as a result of using symbiotic nitrogen. So in here, I'm emphasizing on the bootstrap model because the literature tells us that the results from the bootstrap model are more varied because they take care of the sampling variability and other sampling errors. Yeah.
Why do we have higher technical?
Mm-hmm. Okay, good question. Bias is not in one direction. Bias can be up or down. So if you correct, you can either go up or you can come down. Okay, so then we do the same analysis for intercropping and rotation combined. So the same interpretation again arises. A mean of 0.34 is the distance, which is a measure of inefficiency. And then a 0.41 is also a measure of inefficiency in our bootstrap model. Then we also use the marginal products to get the shadow prices of symbiotic nitrogen. But what we realize here is that if now we have more nitrogen in the pool, so farmers are becoming more inefficient when there is more nitrogen if we account for crop rotation, which is something that most studies don't account for. So what we realize that is the residual nitrogen that is still left in the soil from the previous season, it also has a contribution to the present season production. So if we account for that, then we find that the production system is more inefficient. But in terms of value, the value has increased. Now we have the mean value of 1.25 in the base model and 1.20 in the bootstrap model. So we can use this plot level analysis to generalize into the economy. So we know that in the 2013-2014 crop season, beans occupied about 22,000 hectares of land. So using the fixation rate of 2.77, we can compute that about 60,000 kilograms of nitrogen were fixed in the soil. Then using this price, which we have about $1, we know the value of this symbiotic nitrogen generated by common beans, Phaseolus, is about $72,000. Using the same process, we can compute for groundnut, soybean. So in aggregate, these three crops contributed about $4.3 million US in terms of fertilizer cost savings. So this is near 10% of the agricultural budget in Malawi. So we see that there are also the legume-based cropping systems that are making substantial contribution in terms of fertilizer savings as a form, an alternative form of soil fertility improvements. So in conclusion, in this study, we've managed to come up with an estimate of what the legume-based cropping systems are worth. And then this is a good piece of information that we can use to guide public policy as well as to advocate for legume-based cropping systems as an alternative source of soil fertility. We also realized that using direct market prices, as in other approaches, may not give a proper estimate of environmental services, in this case symbiotic nitrogen, because we know there are price distortions, so we have to take account of that. And then we also noticed that there is inefficiency in the production system. So output expansion is possible using the same inputs, or input reduction is possible to achieve the same output. And again, it is important to account for rotational effects. So rotational effects makes some residual nitrogen, which the crops makes use of. So if we account for that, we find that the production system becomes more inefficient. If we don't account for that, then our estimate would be erroneous. Okay, thank you. So I acknowledge the support, financial support from those 3 awards that was used to support data correction process. So yeah, thank you. And these are selected literature that we used.